Okay, today we're going to talk about conservation of momentum. We've talked about what momentum is. Momentum is a combination of mass times velocity, and it really is a measure of how hard it is to stop something. It's a vector quantity. It does deal with motion, but it also deals with mass. So we're going to explain the law of conservation of momentum, and then we're going to use the conservation of momentum to solve problems, and then we're going to explain the difference between an inelastic collision and an elastic collision. Now, key thing to understand, momentum is always conserved. It's not just a good idea, it's the law. In other words, the total momentum of a system is constant in an isolated system. An isolated system means we're not adding anything from the outside. It's useful in analyzing collisions and explosions. Now, collisions, two objects colliding, Homer Simpson, duh. An explosion is when an object breaks into two or more parts. So in other words, it starts out with an initial momentum of 0. Now we think of explosions, we think of bombs and stuff like that, but it doesn't have to be, and I'll show you an example or two of that. And in all cases, the momentum initial is equal to the momentum final. We can also say the momentum before equals the momentum after. Now, momentum tables are a wonderful way to kind of solve it. Algebraically, these can get a little sticky looking. So by having a momentum problem and by creating a table, it helps you identify all the objects, it helps you list them, and then it helps you solve for the unknown momentums. And of course, one of those is going to contain an unknown variable. So we're going to identify all objects and list them down the left side. We're going to solve for all momenta that are known and use variables for the unknowns. And then we're going to add up all the momentum before and after and set that equal to the momenta after, and then solve for any unknowns. It's probably easier to see by doing an example problem. So we have a 2,000 kilogram car traveling at 20 meters per second. It collides with a 1,000 kilogram car at rest at a stop sign. If the 2,000 kilogram car has a velocity of 6.67 meters per second after the collision, what is the velocity of the 1,000 kilogram car after the collision? So kind of a straightforward collision problem. We have a car that's moving very fast that collides with a stationary car. The moving car continues to slide, but at a slower speed. It lost momentum to the other car. So let's go ahead and look at it. Now, first of all, the momentum tables we talked about earlier will look like this. You'll have a place down the left side for objects. You'll have a place for your momentum before. The units are going to be kilograms times meters divided by seconds. And then you'll have a place for your momentum after, and also it's going to be kilograms times meters divided by seconds. Now, the first thing I have to do is label my objects. So, for example, I'm going to call the car object A, and I'm going to call the other car object B, and I'm going to list those. So I have an object A and an object B. You could also write car and car A and car B in there if you want, something like that. And then, of course, the total. And I know that those two momentums are equal to each other. Now, the momentum beforehand for car A is 2,000 times 20, so 40,000 units of momentum. The momentum of car B before is 0 because it's at rest. Now look for keywords like rest and stop because they will help you. So I know that beforehand I had 40,000 units of momentum. That's all I can have afterwards because they have to be equal. Now let's look at the after side of the equation. Now for the after side of the equation, the 2,000 kilogram car still had a speed of 6.67 meters per second. We have to assume it was in the same direction. It didn't say anything about it bouncing and going the other way. And then what we want to know is the velocity of the 1,000 kilogram car afterwards. So the momentum of the 1,000 kilogram car after is 1,000 kilograms times the velocity of B. Remember, that's what I don't know. The key thing though is I know those numbers have to add up to 40,000 because momentum has to be conserved, always conserved. Now let's set about trying to solve it now. I'm going to say 13,340 kilogram meters per second plus 1,000 times VB has to equal 40,000 units of momentum. So 1,000 VB is equal to 40,000 minus the 13,300, which is 26,670. Divide both sides by 1,000. I get that VB is equal to 26.7 meters per second. Now, see if that makes sense. You have a fairly large car traveling at 20 meters per second, and it hits a very small car. Would we expect the small car to move off at a faster speed? Yes. So that does make sense. Our numbers back it up. Okay, let's take a look at another. Now, on a snow-covered road, an 1,100 kilogram car collides head-on with a 2,500 kilogram truck traveling at 8 meters per second. Not good. After the collision, the two cars lock together and immediately come to a rest. Calculate the car's speed before the collision, and we're going to neglect friction. So again, fairly straightforward, except now they're coming directly at each other. So we're going to start by drawing a table. We have our objects, momentum before, momentum after, and I know those two are equal to each other. That's kind of the key to solving these problems. Now, beforehand, object A, I'm going to call the car, 1,100 kilograms. You could just write car and truck in there if you want instead of A and B. And B is going to be the 2,500 kilogram truck. I also want to know the total momentum. Key thing is head on, so that means the directions are opposite, so I have to take that into account. Now, my momentum before for car A is 1,100 times VA. I don't know that. That's my unknown. Afterwards, for car B, my momentum is 2,500 kilograms times 8 meters per second. But remember, they're colliding head on. So either VA or 8 meters per second has to be negative. It doesn't really matter which one you call negative. Now I'm going to call the truck having a negative velocity, but it really does not matter. Now here's the key thing. After the collision, the two cars lock together and immediately come to a rest. If they immediately come to a rest, we know the momentum afterwards is zero, and it's zero for everything. The truck stopped, the car stopped, both of them stopped together. If that's zero, we know that that's zero. So we have two numbers adding up to zero. Obviously one of them has to be negative. That's the reason that direction had to be negative earlier. So I'm going to say 1,100 times VA is equal to, plus 2,500 times negative 8 is all equal to zero. Move the 2,500 times the negative 8 to the other side, and it becomes 1,100 VA is equal to 2,500 times positive 8 when I move it to the other side. So therefore VA is equal to 18.2 meters per second. Now, does that make sense? That the car would have to be traveling faster than the truck? Well, to have the same momentum, it would have to. The car is smaller, so therefore it would have to be traveling faster. So the math backs up what our brain thinks. Okay, let's take a look at an explosion. And this is an example of an explosion which is not a traditional bomb exploding. What we have is a recoil velocity of a rifle, common type of physics problem. And if you think about it, if you've ever fired some type of rifle for target shooting or something like that, if the bullet goes one way, your body wants to go the other way. So here's one. A 4-kilogram rifle fires a 20-gram tranquilizer dart with a velocity of 300 meters per second. Find the recoil velocity of the rifle. Now, first of all, before we start any math, let's make sure we kind of understand this. We know that momentum before is equal to momentum afterwards. That's the law. Has to be valid all the time. So we know beforehand I had a momentum of 0. That means afterwards I have a momentum of 0. So the dart went one way, my body went the other way. And the momentums are equal to each other. Remember, momentum is a vector quantity, so the dart's momentum has to equal the gun's momentum. Okay, now let's work on trying to solve it. Start by our table. Okay, A will be the rifle, B will be the dart, rifle, dart, and total. And again, if you want to call them A and B, you can. If you want to call them rifle and dart, you can. Either one. Now let's go just try and figure out the momentum beforehand. Well, I have 4 kilograms times 0, so before I have no momentum in the rifle. The dart, 0.02 times 0, it also has no momentum beforehand. So my total momentum beforehand is 0. That means I have to have a momentum of 0 afterwards. 4 kilograms times the velocity of the rifle is the momentum afterwards. I don't know the velocity of the rifle, that's my unknown. I do know enough for the dart. 0.02 kilograms. Remember, your units have to agree. So I'm going to take 20 grams divided by 1,000 kilograms, 1,000 grams per kilogram. It gives me 0.02, and I know it's moving at 300 meters per second. I know all of that has to add up to 0. So let's take a look at the math. 4 kilograms times VR is equal to 0.02 times 300 meters per second. 0.02 times 300 is 6 kilogram meters per second. 6 kilogram meters per second divided by 4 is 1.5 meters per second. So you and the gun rock back at 1.5 meters per second afterwards. So here's an explosion problem that doesn't involve something blowing up into pieces. Now, there's two different types of collisions. Now, we really haven't talked about kinetic energy a whole bunch yet, so we're not going to do any math with this right now until after we talk kinetic energy. The two types of collisions are an elastic collision, and those are bouncy collisions. Pool balls on a pool table are fairly elastic. That means that not only is momentum conserved, but all kinetic energy is conserved. Now, in a completely inelastic collision, the two objects colliding stick together. This would be like a snowball hitting a moving vehicle or something like that. The colliding objects are then going to slide together, and therefore you have lost kinetic energy. It shows up in another form. We never lose energy, but it just shows up in another form. But we'll spend more time talking about those later. I hope this helped.